Neural networks were invented years ago, but they could not generate real images because they did not know what real images or real objects look like. That was a huge problem. So researchers came up with a method to generate images using neural networks, and that is known as diffusion models. So AI needs to learn how to generate new images, but a neural network does not know what an image or what an object looks like. It only sees numbers. It only deals with numbers and vectors. You can't just tell a neural network to draw me a cat and expect a cat in return. It simply does not happen. So the question is, how do you teach a machine to generate a new image? The answer is, destruct the image and teach the neural network how to undo the destruction. Listen to it again. Destruct an image and teach the neural network how to undo the destruction. That is diffusion models in a nutshell. Here's the idea. Take thousands and millions of images and destroy them, step by step, into TV static. Each step adds a tiny bit of Gaussian noise, small, predictable, and mathematical. After 1,000 steps, nothing visible remains. Only noise. There's no real image. You can see nothing in the image. But you have a lot of training data. Now you have infinite training data. Every image at every noise level is a lesson. It's data for the neural network to learn. So, how do you actually train it? You show the neural network two things. One is the noisy image, and the second is time step t. So, basically, in simple words, it looks something like this is what the noisy image looks like at XYZ step. This is what the noisy image looks like at 984th step. We'll do this for every image at every step. Just imagine how much data it would be for the neural network to learn. And then you ask it one question. What noise was added to every single pixel here? And then it predicts a noise vector for each and every pixel. It tells us how much noise was added to every pixel in vector format. So for a 256 by 256 pixels image, it will be like 2 lakh or 200k. 200k predictions, 200k vectors, 200k numbers in simple words. You compare that to the actual noise that was added, and then you calculate the difference, update the network, and repeat this a million times. And slowly and steadily, the network learns how real images are formed, what real images look like. The network learns what real images look like at every noise level. No labels needed. The destruction process itself is the training data and signal. Okay, so now the fun part. Generation. Image generation. You start from pure TV static, nothing hiding inside, just random numbers and noise. The network looks at the static and predicts what noise was added to the time step t is equal to 1000, and then it subtracts it. So now we are at t is equal to 999. We do the same process here. Subtract the noise. Now we are at t is equal to 998. And it keeps repeating this until t is equal to 0. And then finally, we get a new image. New real image. At t is equal to 0, we'll get a brand new image that never existed before. And here's the thing that blows most people's mind. No image was hiding behind the noise. The network just knows what real looks like, and it keeps nudging towards it, pixel by pixel and step by step. So everything so far was basic diffusion. No labels and prompts were included. Neural networks just generated a random new real image. And now, stable diffusion comes in, or we can call it clip plus diffusion. Clip is a separate neural network trained on millions of image and text pairs, and it learns to map both the texts and images into the same vector space. So a red cat as a text and a red cat as an image both become a vector, and they are located very close to each other in the vector space, and the cosine similarity very close to 1. Now at every single denoising step, we keep injecting that text vector, and the network keeps asking, is what we are generating actually close to the text vector? And if it's not, correct it. So the image gets sculpted to your direction, to the text prompt you provided, very close to it, every time, 1,000 times. So let's bring it all together. No image was hiding in the static. The network just knows what real looks like after training on millions and millions of images. And then it keeps nudging it toward that step, toward the real image, until something real emerges out of nothing. The forward process in diffusion models is basically turning a real image into pure noise. And then the backward process is turning the noise into a real image. Add clip to it, and then cosine similarity steers the image generation to your prompt at each and every step. Let me show you an image that I created in XCaliDraw that explains the forward and backward process visually in a very simple manner. As you can see in this image, forward process, it's a real image here, and then we add noise to it, and then the real image turns into pure noise. This is what forward process is. Images are purposely spoiled and noised, and it is made sure that nothing is visible in the frame. This is known as forward process. And this is the real magic, backward process, where the real image generation happens. This is t is equal to 1000 steps, pure noise. And then gradually we go to t is equal to 500 steps, where approximately half of the noise is eliminated by subtracting the vector predicted by the neural network from the noise of each and every pixel. And then eventually we achieve t is equal to 0 steps, where we get a new real image. A neural network is trained to predict the noise vector added to every pixel, so it learns what real images look like. Then it starts from a completely random noised image or TV static. Step by step, it denoises the image, subtracting the predicted noise vectors from every pixel. Dang, we got a new image. This is the whole world of diffusion models explained in a nutshell, explained in a very intuition maxed way and very simple manner. It's not as simple as it looks. The physics and math behind it is very complex. But this is what it looks like from the above, from the front end, from the architectural view. So this is what diffusion models are.